Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 21. We are in lecture 8, part B. This is part 4 of simple regression. Up to this point, we have reviewed the least squares regression line from earlier in the semester, talked about a simple linear regression, derived the least squares estimators, and discussed and defined the residuals and fitted values. So in this video, we are going to develop the maximum likelihood estimators, and we will see how far we get. So let's get started. All right. So recall that our line is yi equals alpha plus beta times xi minus x bar plus epsilon. Now, I want to point out about this epsilon. We use this when we use population parameters, not estimators. So this is a theoretical model that we do not know, okay? Now, when we use a data set to calculate the estimators, then we end up with yi hat equals alpha hat plus beta hat times xi minus x bar. There is no epsilon because epsilon has been incorporated into the estimators. There is error there, and so that error is taken into account by the sample and therefore ends up in these estimates. So the least squares estimates. All right. Now, we have this model and we say that these are independent, right? So the yi's are all independent. So that's a very important assumption. And the epsilon i's are normally distributed with a mean of 0 and a variance of sigma squared. Now, what we have here is a model for every single value of x. So for every single value of x, there is a normal distribution of errors. Okay? So what we see here, if we have this, it's supposed to be a straight line. If we have this this best fit line here, for any value, I'm going to move up so I can get my hand on my iPad. Say for x1, then for x1, we have a normal distribution. And then, let's say for another value of x, x2 we'll call it, we have another normal distribution. Okay? So for every single value of x, fixed value of x, we consider there to exist a normal distribution. And the errors are what's normally distributed about this. And so because the errors are normally distributed with a variance of sigma squared, notice that there is no I here. It's not an I. We're saying for any value of x, we have a common variance. So that's a very important assumption. And these are assumptions that we have to verify. The normality of the distribution and the equality of the variances for all values of x. Those are assumptions that have to be checked in real life. Okay? So as applied statisticians and data scientists, you don't want to ignore that. So let's look at yi. What we have here is, we have a constant. This is a constant. Alpha is a parameter, it's a constant. Beta is a parameter, it's a constant. X sub I is a fixed value that we can set, therefore a constant. And then x bar is a constant value as well, because once we have x bar, it's set. So the variable part of this equation is the epsilon I, and it's normally distributed. So yi is equal to this constant plus a normal random variable, epsilon, that has a mean of 0. Okay? So if we want to find the expectation of yi, this is going to be the expectation of this constant plus the expectation of epsilon, and its mean or expectation is 0. So we're left with the line as the mean of y. Okay, so the fitted value, and this fitted value, actually this is not a fitted value. The line, the fitted line, least squares line, is the mean of the y for each value of x. Now I can do the same thing with the variance. And here what I'm going to do is pretend that or break this up and say that the line portion is one part, it's all a constant, of a sum. And so I could think of this as like A and this is like B. So I've got A plus B. And if I take the variance of A plus B, then that's going to be the variance of A plus 2 times the covariance of A with B plus the variance of B. Well, A is a constant, so the variance of a constant is 0, and the covariance of anything with a constant is 0. So all I'm left with is the variance of epsilon, and its variance is given right here as sigma squared. So the variance of y is sigma squared. So what this means is that yi is normally distributed with a mean of alpha plus beta times xi minus x bar, comma, and variance sigma squared. So here's my mean, here's my variance. So by using this information, we're going to find the least squares estimator, or not the least squares, I'm sorry, the maximum likelihood estimator. We've already have the least squares estimator. Now we're going to find the maximum likelihood estimator of alpha, beta, and sigma. So if yi is normally distributed with a mean of alpha plus beta times xi minus x bar and a variance of sigma squared, then we can write the PDF as 1 over the square root of 2 pi. This is sigma squared. So instead of having sigma times 2 pi, we've moved that inside the square root. So to do that, we have to square it, because the square root of the squared is just sigma, okay? And then we have exp, and we have yi minus its mean. Its mean is given right here. We're subtracting, so we'll have a subtraction here, and that will become negative as we distribute that negative sign. And so that is, and then that divided by 2 sigma squared in the denominator. So we need to find the likelihood function. These are independent. So the likelihood function is simply the product of these distributions for different values of xi and yi. Okay. Now, I want to point out that I can rewrite this fraction here. This is the same thing as 2 pi sigma squared to the negative 1/2. So if I'm going to take the product from I equals 1 to n, this is all constant. There's no subscript I here. There's no index for it to change. They're all the same. So this is going to be itself multiplied n times. N pi sigma squared to the negative 1/2. 2 pi sigma squared to the negative 1/2. Up to the nth time, 2 pi sigma squared to the negative 1/2. So there's going to be n of these. So it's going to be 2 pi sigma squared to the negative 1/2 raised to the nth power. And when we raise an exponent to a power, we multiply the exponent. So we get 2 pi sigma squared to the negative n over 2. Okay? So I wanted you to know how I'm getting the next term. And then when we multiply, remember exp is the same thing as e raised to this quantity. It's just a different way of writing it so that we don't have to discern between what's an exponent and what's not. Okay? And when we multiply bases of e and they have their exponents, we add the exponents. So we sum up these exponents. So we add them together. And so we're going to end up with a summation inside the exponent. A summation of the e, exp. We're going to, I always say exponent, but it's really the base e raised to the power. raised to an exponent, okay? The natural number raised to a power. And so when we take this product, we're going to end up with 2 pi sigma squared to the negative n over 2, and then times exp, and then we have the sum. Now, when we are adding, I've got 2 sigma squared over something plus something over 2 sigma squared plus 2 sigma squared. That's a common denominator. We do not add the denominator, right? We add what's in the numerator. So we're going to end up with the same denominator, but in the numerator we're going to have that negative, and then the sum of, and we're going to have yi minus alpha minus beta times xi minus x bar, and I can't forget the square. I've forgotten the square up here. I probably corrected myself and then erased it and then forgot to put it back. But there is a square there because it's y minus its mean square. Remember, it was if we were using x, it would be x minus mu of x, quantity squared, negative, over 2 sigma squared. And so we have to have that same pattern here. So we can't forget the square. If we forget the square, we don't do a very good job of taking the derivative when we get there. Okay. So this goes from I equals 1 to n. And now we're going to take the log. So L of alpha, beta, sigma squared. And I can put sigma squared instead of sigma there. And then I'm going to take the log. And so this is going to be negative n over 2 log of 2 pi sigma squared. Now, I'm not going to worry about expanding this right now. I could make this negative n over 2 times the log of 2 plus negative n over 2 times the log of pi plus negative n over 2 times the log of sigma squared. So I could do that, but I'm not going to expand it to that level. I'm going to leave this together, especially for alpha and beta. When we're taking the derivatives with respect to alpha and beta, there's no alpha or beta in this term, so it's going to go away for that. So take the log of e raised to a power, the natural log of e raised to the power. We'll just end up with its exponent. So this is going to be minus sum, and I will use brackets, square brackets, yi minus alpha minus beta times xi minus x bar, quantity squared over 2 sigma squared. Now I'm going to take the derivative with respect to alpha. And again, the first term is going to go to 0. So I have 0 minus. Now, remember, I can rewrite this as 1 over 2 sigma squared, or negative 1 over 2 sigma squared times the sum of what's in here. And so I can pull this constant out of this because there's no alpha or beta here. So this is 1 over, 1 over 2 sigma squared, and then the derivative of the sum is the sum of the derivative. So I'm going to take the sum, and now I have a function squared, so I'm going to take 2 times the function yi minus alpha minus beta xi minus x bar, and then times, use the chain rule, I'm going to take the derivative of the function with respect to alpha. But this is just going to be 0 for y, and then a negative 1 for alpha, and then a 0 because there's no other alphas over here in this portion. I'm going to get rid of my underline here. Okay, so this is going to be 0 minus 1 minus 0. Okay, and so what I have is negative 1 over 2 sigma squared. And then I can pull the 2 out, so this can become a 2. And so those will cancel. Sum of, and I have a negative 1 here, so this whole thing is a negative 1, so that will make this positive. And then I will have yi minus alpha minus beta xi minus x bar, quantity. And so I can say that this is equal to 1 over sigma squared sum of yi minus alpha minus beta xi minus x bar. and I can set that equal to 0. Now, this is just a constant, so it will never be 0. And I could divide both sides by this, 1 over sigma, or multiply both sides by sigma squared. Or I can just say, okay, that's one term. It can't be equal to 0. So what must be equal to 0 is this summation. So I'm going to set this summation equal to 0. And now I can distribute the summation. I'll have the sum of yi minus the sum of alpha, but there's no alpha I. It's just alpha. It's a constant. And this is going to be alpha, and there's going to be, I'm going to do that n times. So there's n of these. So I'm going to have n times alpha is what that quantity is going to be. When it's a constant and you're summing, you can just take this and multiply that by what you have, as long as you're starting at 1 now. If you're not starting at 1, then you need to count to see how many terms there are. And then you can take the number of terms times the constant. In this case, we're going from 1 to n, so this will be n times alpha when we simplify. Minus, beta, again, doesn't have an index, so I can pull it out to the front of the summation. So beta, sum of xi minus x bar, equals 0. Now, this term is going to go to 0 because the sum of xi minus x bar is always 0. Okay? So I end up with the sum of yi equals n times, minus, jumping ahead, n alpha equals 0. So I can add n alpha to both sides, and I get n times alpha equals the sum of yi. And so now I divide both sides by n, and I end up with alpha equals the sum of yi over n, which is y bar. I need to determine if this is a max or a min. So I need to take the second derivative of L. I'm going to note that this term goes to 0. When I take this summation, I can still have 1 over sigma squared, the sum of yi minus n alpha minus 0. So this is partial L, partial alpha. Okay? So if I need to take the second derivative, I want to use the simplest form, so I'm going to use that in the box. So the second derivative, alpha, equals, I've got the constant in the front stays, and then there's no alpha in the sum of y, so that's 0, minus n. So the derivative of n times alpha is just n. And this gives me negative n over sigma squared. Sigma squared is always positive. Any squared number is always non-negative. Okay? And so this has to be, and n is always positive. My sample size has to be 1, 2, 3, etc. So this is always less than 0. And that means that we are concave down, and we've set the derivative equal to 0. That means we have the maximum. Okay? So, which implies alpha hat equals y bar is the MLE. Okay? So we've found the MLE of alpha hat. So I'm going to write that alpha hat equals y bar is MLE. So I'm going to find the MLE of beta. So I have the same likelihood function. So now I want to find beta hat, MLE of beta. So now I'm going to take partial L, partial beta. And so again, this first term doesn't have any betas in it. So it's going to be 0. And then minus, and again, I can pull the 1 over 2 sigma squared out to the front. I can then take, and I've got this square, don't forget about that. And the derivative of the sum is the sum of the derivatives. That's something you should learn in Calculus 1. And so I can take the derivative inside the summation. With respect to beta, that's going to be 0 minus, and then I've got xi minus x bar. Oh, I'm sorry. I've got 2. I'm doing the chain rule portion first, and I should not. So I take the power 2 and put it in the front, and then I have yi minus alpha minus beta times xi minus x bar, and then 2 minus 1 equals 1, but I don't need to put a 1 as an exponent. That just means it's itself. And now I'm going to take the derivative of the function. That's the chain rule. And so I take the derivative of that with respect to beta, and it's 0 minus 0 minus. This is a constant with respect to beta, so it can come out to the front, xi minus x bar, and then the derivative of beta with respect to itself is just 1. So I'm left with this quantity. Okay? And so this is equal to negative 1 over 2 sigma squared. And then I can, this has to stay inside the summation, but I can pull the 2 out. So I will have a 2 here. And this is negative. So this quantity here is going to be a negative xi minus x bar. I can pull the negative out to the front too, so that will make this whole thing positive. I can get rid of that 2 and that 2. They cancel. And then I will have the sum of, and I can put xi minus x bar. I can put this in the front. And then yi minus alpha minus beta times xi minus x bar. Okay? Now, so to do this, I can, what I'm going to do is I'm going to distribute this. I'm going to group yi minus alpha together. And I'm going to distribute the xi minus x bar across these 2 different terms. I'm going to consider this one term and this another term. And so this is going to equal 1 over sigma squared sum of xi minus x bar times yi minus alpha minus, I'll put a big bracket there, minus the sum of beta times xi minus x bar quantity squared. So I have distributed the summation across this negative here, and I've distributed xi minus x bar. Okay? So now I can substitute in for alpha. I've solved for alpha. Remember, this is a system of equations, so when I solve one variable, I know I have to use it to solve the other, just like any system of equations. Once we find out one of the values, we can plug it in to the other equations because it's the same in all of the equations. So I'm going to plug in for alpha y bar because that's what we found. So it's 1 over sigma squared times the sum of xi minus x bar times yi minus y bar, and then minus the sum of, I can pull beta out to the front, xi minus x bar quantity squared. I'm going to set that equal to 0. Well, again, this is just a constant and it's positive, so I can't set it equal to 0. But this other product, or the other term of the product, I can set that equal to 0 and see. And so before I do that, I'm going to simplify, because by simplifying this, it makes it easier when I take the second derivative. So I've got equals 1 over sigma squared, and then I'm going to use a trick. I'm going to distribute yi minus y bar across xi minus x bar. Okay? So I'm going to have the sum of yi times xi minus x bar minus y bar times xi minus x bar. And all of that is going to be inside that summation. And then I have minus beta times the sum of xi minus x bar quantity squared. And, yep, and that's still equal to 0. And now I can distribute this summation, sigma squared. I'm going to have sum of yi xi minus x bar. Now the y bar, when I distribute the summation, it doesn't have any index. I can pull it out to the front of the summation, and I have xi minus x bar. The sum of xi minus x bar, that's 0. So this term goes away, and I have minus sum of xi minus x bar quantity squared. And so this leaves me a first derivative of 1 over sigma squared times the sum of yi xi minus x bar minus beta times the sum of xi minus x bar quantity squared. That's equal to 0. Okay? So this is my derivative, my first derivative here. Or not with a 0, but with... That's my first derivative. This is L, or partial L, partial beta, or the derivative of L with respect to beta. And so now I need to set this summation equal to 0. So I have the sum of yi xi minus x bar minus beta sum of xi minus x bar, quantity squared, equals 0. So that means I can add this to both sides, and I'll end up with, I'm going to cheat here, it's xi x bar squared xi here. I'm just going to set the equal there now. And I need to solve for beta, and so I'm going to get beta is equal to the sum of yi times xi minus x bar over the sum of xi minus x bar squared. Now, I showed you that this summation is the same thing as the sum of yi minus yi minus y bar times xi minus x bar. Okay? So I can write it that way, and that's the preferred way, yi minus y bar xi minus x bar. And we don't care if you put the x first or the y first. This is the maximum likelihood estimate. Or so the MLE is the same as the least squares estimate. Now we need to prove that this is in fact a maximal. And so I'm going to take the derivative here with respect to beta again, and I get the 1 over sigma squared out in the front, because remember, a constant times the derivative of a constant times the function is the constant times the derivative of the function. And so I take this with respect to beta. This whole first term here is 0 because there's no beta in it. So this is going to be 0. And then I have minus. And then I'll have, remember, with respect to beta, this quantity, this summation, is a constant. So I take the derivative of beta with respect to itself, it's 1, and I end up with negative sum of xi minus x bar quantity squared. And so this is the negative sum of xi minus x bar squared over sigma squared, which is less than 0 because these are squared values. They're all positive. This is a squared value. So the numerator is positive, the denominator is positive, and then I'm multiplying the whole thing by a negative, so that's less than 0, which implies that beta hat equals the sum of xi minus x bar quantity yi minus y bar over the sum of xi minus x bar quantity squared is the MLE of beta. I need to join down here with my summary. Beta hat is equal to the sum of xi minus x bar yi minus y bar over the sum of xi minus x bar quantity squared. So that's beta hat, the MLE. And this is the MLE. So the least squares estimate and the MLE are the same. All right, that's it for this video. I hope you've enjoyed it. If you have questions, then please come to virtual office hours, and I'll be glad to try to point you in the right direction. If you need help before you can make it to virtual office hours, then by all means email me, and I'll do my best to help you through email. and I'll respond to you as soon as it's possible. Please take care of yourself so we can see you next time.